Okay, so we will keep going. Okay. Okay. We were in the middle of this. Orthogonal diagonalize. Okay, so we were kind of in the middle of this last time. Okay, so we will just continue. Lambda equal to 7. Okay. We need to find this matrix D. Okay, this is the matrix D. It's going to be 7 minus 2. Okay, that's the matrix D. And the matrix P will be eigenvectors. Okay, we want to find 3 orthogonal eigenvectors. These guys are all going to be orthogonal already from these two. Yeah, it works out. Yeah. But V1 and V2 are not orthogonal. And we're going to try to get a V2. Okay, so we want to find a vector. What should I call this? Find a vector U. Find vectors U1, U2 in the eigenspace for 7. Okay, such that U1 of U2 is equal to 0. So we want to find a pair that's orthogonal. How do we do that? We use the Gram-Schmidt process. So U1 is going to be equal to V1. Okay, and U2 is going to be equal to U2 is going to be equal to V2 minus, okay, V2 minus the projection, of V2 onto U1. Okay. Do you guys know what I'm doing? This is Gram-Schmidt process. Hopefully it's correct. Are we okay with this?
Yes.
So my U1 is equal to 101. Okay. If you like, you can use V2 equal to -120. Okay. Okay. Do you guys understand why I can use that? I can just scale it. It doesn't really hurt. Then I don't have to deal with the fractions. Okay. So make sure I do it right. I'm deviating from my notes a little bit here, probably. Okay. So I'll try to do it slowly to do it correct. This guy is the projection onto U1. Okay, I think this is correct. This dot product, what's that dot product? -1. -1 over what? 1 square plus 1 square is 2. So there's a minus sign here. Okay. So it's -1 plus, okay, I'll write one more step so I can do this correctly. Are we okay? So I can use U2 equal to, I don't like the fractions. Okay, I don't like the fractions. So multiply by 2, this will be -1, 4, and 1. Okay, so now I have this. Okay, I have 3 vectors. Okay, I have 3 vectors. These 3 vectors are -1, 4, 1. The first one is 101, 101, -4. This guy and this guy. V3. V3 here. V3 I'm going to use -2, 1, 2. Okay, let's check whether these are all orthogonal to each other. Hopefully they are. They are not though. See, I mess up. Okay. So what did I do wrong? -2, 1, 2. Okay. So these 2 are orthogonal. Okay. These 2 are orthogonal. But the last one is the last one. The last one doesn't work. I mess up somewhere. Okay. Have to figure out where I mess up. -141, that's correct.
So someone comments it, I think.
V1. Okay, so this is the third one. Oh, this is minus. Okay, okay, this is good. Okay, so we are good. Okay, okay, so those are the three vectors. Can you check that these three are actually orthogonal to each other? These first two, okay, these first two are for lambda equal to 7, and this guy is for lambda equal to -2. Any question? You guys know what we just did? We take the two vectors in the eigenspace corresponding to lambda equal to 7, and we basically take two perpendicular ones using the Gram-Smith process. Okay? Now, so these three vectors are eigenvectors. Okay, we usually just put that there as columns, and that will get us the P. Okay, but now because we want this to be orthogonally diagonalizable, we want P transpose equal to P inverse. So we need one additional property. What would be the additional property? In addition to this guy being pairwise perpendicular, I also want it to have unit length. So in order for this guy to be unit length, what do I do to make those guys unit length?
Divide by the magnitude.
Divide by the magnitude. So these guys, instead of those, I will have to modify it. The magnitude of this guy is going to be square root 2. So 1 over square root 2, 0, 1 over square root 2 is the first one. Okay, the second one. The second one is square root of 18, 3 root 2. Okay. The third one, 9, square root 9 is 3. Okay, that is my matrix. Okay. This is my matrix. So I have my answer. Okay. I have my answer over here. I'm running out of space. P is equal to 1 over 2, 0, 1 over 2, minus 1 over 3 over 2, 4 over 3 over 2, 1 over 3 over 2, minus 2 over 3, minus 1 over 3, 2 over 2. Okay. So it has this property now. A is equal to P D P inverse. P inverse is the same as P transpose. Okay. So any questions so far?
P. Oh, never mind.
You were saying something, Eva?
Or how come we want to orthogonally diagonalize something?
But that's okay. How come we want to do that?
Yeah.
Oh, okay. It's coming up. Next section. Next section is coming up.
Okay.
It will explain to you. Okay, orthogonally diagonalize means that. Okay, let me answer that a little bit. This P matrix, essentially, if you look at it as a linear transformation, it is going to be an isometry. That means it preserves the angles and it preserves angles and preserves lengths. Okay, that is the property of orthogonal matrices. So essentially, we are looking at some kind of change of coordinate system or substitution, where you reorient whatever you have in space so that, let's say, rotate or something, so that it will look nicer. Okay, which is come up in the next section. So orthogonal matrix, I mentioned it last time at one point, maybe not last time. So it preserves inner products. Okay, so if I have, let's say, I have U1 and U2. Okay, and then if I consider P times U1 and P times U2, okay. Now this is essentially when you multiply by a matrix, it's basically transforming, doing something to it, or moving to a new coordinate system. Okay. Now what I want to show you is that PU1 dot PU2, this dot product is going to be the same as U1 dot U2. Okay. I'm going to try to show you that. If P is this is under the assumption if P is an orthogonal matrix. Okay, so how do I show this? We just start out with here. A dot product can be written as the transpose of this guy times this guy. These are both column vectors. These are both column vectors, two columns. When you write it like this, you have this row times this column as matrices. Then you do the transpose. This one become U1 transpose P transpose PU2. The P transpose and P is equal to I. This one is I, identity. So this one is become U1 U2. So basically preserving inner product, because inner product is used to define length. Something dot itself is the length square. Inner product is essentially determine the length and the angles. Okay. So when this is preserving the inner product under the transformations. Okay. So you have two vectors, U1 and U2. They have some relationship. You do something to this, and you do something to this. Okay. Both of them are under some transformations. Or you can look at it as a change of coordinate system. Then this guy, if these two dot equal to 0, this guy dot is equal to 0. Okay. Or basically the dot of these two is the same as the dot of these two. So the inner product doesn't change after you do the transformation for each of those two vectors. The next section is going to illustrate this very well. Okay, so we are going to go to the next section now. 7.2, this is the last section. Oh, by the way, we actually still have class next week. Unlike some of the UCs, which has a dead week, you don't actually have class. We still have class next week. But hopefully, I don't have to teach a lot of new material. I'll be really done with 7.2 today. Okay? And then we can do review, or you guys can ask questions. Okay, any question? Okay, 7.2. Quadratic forms. Quadratic forms has to do with, it's kind of like generalizing the conic sections. Do you guys remember you learned conic sections in high school? Some of you probably did. You have something like this. This is the equation of anybody know this?
Circle?
Circle, when A is equal to B, will be a circle. When A is not equal to B,
Ellipse.
did someone say something? Luca, you say
Is it
something?
an ellipse? Yeah.
Yeah, it's
Is
an
it-
ellipse. Anyone know this? Ellipse is encompass circle. Circle is just a special case of ellipse. Anybody know this one? Ellipse, of course, is not something like this. This is called a. Okay, you guys don't know. Some of you did calculus 3 should know. Hyperbola. It's a hyperbola. It typically look like this. Sometimes it's rotated 90 degrees, but this one is like this. This is coming back to some of you? No?
A little.
Okay. So quadratic form is actually, I mean, this thing when you generalize with 3 dimensions, you can generalize it to 3 dimensions. Then it becomes ellipsoid and all this other stuff. I'm not going to get into that too much, okay? Because we'll do a lot more on that on calculus 3. Hyperbolic paraboloid, elliptical parabola, and all this stuff. Okay, so this is essentially a generalization of all this stuff. Okay, so let's take some example here. What's X transpose AX? X transpose is X1, X2, A is this guy, and X is this one. And this one become, what does it become? Can you guys see this? Can I skip some steps? Can you guys see that? Because this guy is diagonal, there are no x1, x2 terms, there are no cross terms. Okay. This will become x1, x2, 3x1 minus 2x2 minus 2x1 plus 7x2. This become 3x1 x1 square minus 2 x1 x2 minus 2 x1 x2 plus 7 x2 squared. Okay. This is called a quadratic form. So all terms has degree 2. All the terms, x1 square, x2 square, x1, x2. That is called quadratic form. Okay. You guys understand the definition of quadratic form? Hopefully, basically all the terms, you have these variables. You can have more than 2 variables. Okay. You can have like 3 variables. In that case, the matrix will be 3 by 3. All the terms has degree 2. So let's do an example here. So we have to get the matrix A here based on the, it's kind of the reverse of this process. Now, in order to do that, let's look at this earlier example. Let's look at the earlier example. This 3 here come from the 3 here, the diagonal entry. This 7 here come from this 7 here. And this minus 4 come from the minus 2 and minus 2 together. The minus 2 and the minus 2. Okay, so in order to write this guy as a x transpose AX, the way to do this is that this is my A. Hopefully you understand the process. I'm going to explain to you. This is 5, 2, 5, 3, and 2. Do you guys understand why I have 5, 3, and 2? It corresponds to this 5, 3, and 2 here. Now this term here is going to be the negative x1, x2. Okay, just like here, negative 2, I get negative 4. This term here, this is first row, second column. Second row, first column. So I want to get this number, which is negative 1, and divide by 2. Do you guys know what I just did? Take this coefficient of x1, x2, divide by 2. How about this one here? What do you think is I could put here?
4 and 4.
4 and 4. Very good. How about over here, the missing one? Is there any x1, x3 terms? So we put 0. Okay, So this is a matrix that where A is okay. So the quadratic form can be written in terms of a symmetric matrix. Okay. You guys have any questions so far? Otherwise, we are going to do an example which will essentially answer Eva's question earlier. She has this question, why do we want to orthogonally diagonalize stuff? There are also many other applications. This is just quadratic form, it's just one application. There are many, many other ones. Okay, so we're going to do the next example. Okay. Okay. So I want you to eliminate the cross term. Eventually, I will draw you pictures and so on to understand geometrically what's happening, okay? But for now, we just go through the process. This guy, I am going to write this as X transpose A X. What would be, can you tell me what would be A? I'm going to put it here. Can you guys tell me what would be the matrix A based on what we just did earlier? The first entry here.
1.
This other one will be here. How about the off diagonal? Will be -4, half of -A. Okay. Now what we are going to do next, okay, is to do the following. We are going to diagonalize this guy. We're going to write A as P D P transpose, where P is orthogonal and P is diagonal. So basically, we want to orthogonally diagonalize it. Okay. Let's just go ahead and do that. Okay, so it will be a little bit long, but we can do it. Okay. Okay, maybe I assume that I do this already then. Okay. What's the best way to proceed? Okay, I'll just do it first. We'll just do it. Okay. So how do I do this? eigenvalues. How do I do eigenvalues? Determinant, this guy. Is that right? Is that correct? You guys need to help me, okay, to make sure I don't mess up. Do you want me to go through the detail, or do you want me to just give you the eigenvalue and eigenvectors? You guys can tell me how much detail you want me to get into. I mean, we know how to do eigenvalues and eigenvector, do we?
Yes.
So can I just say what the eigenvalues and eigenvectors are?
Yes.
Okay. So we have lambda equal to 3, okay, and lambda equal to -7. Okay, so those two are different. These two guys are different. So it's guaranteed that these guys are going to be orthogonal. Okay, the eigenvectors, eigenvalues, and eigenvectors. It's guaranteed these are orthogonal. Okay, so we have V1 is equal to 2 over square root 5 minus 1 over square root 5. And here V2 is equal to 1 over square root 5, 2 over square root 5. Now, both of these are unit vectors. They are both length 1. And you can easily check that they are orthogonal. It's guaranteed by construct. You don't need the Gram-Smith here because these two are distinct. Okay. So based on it, yes?
Is it because A is symmetric?
Because A is symmetric. Yeah. Why is A symmetric? The way that we construct it forces it to be symmetric. Is that right? The way that we do it, we take this thing and divide by 2. Okay. So by definition, it is symmetric. Symmetric matrix is always orthogonally diagonalizable. Sometimes you have to go through Gram-Smith process. In this case, the eigenvalues are distinct. These are guaranteed to be orthogonal. All you need to do is to get the unit vector, divide by the norm. Okay. So what will be my D? D is the diagonal entries. D has what are the diagonal entries of D?
3, -7.
-7. What is my P? P is just these two vectors line up, put them in column. Now notice that P inverse is just P transpose. Okay. So now I actually have this. I have this guy here. This guy here. Okay. It's going to be equal to, what's it equal to? This guy is going to be X transpose. P, D, P transpose. X. Okay. Now we are going to do this. We are going to do this. We are going to call this thing. This thing is we're going to call Y. So here's the substitution. Here's the change of variable. Okay. So the change of variable is y equal to p transpose x. Change of variable is similar to change of coordinate system, because when you write y equal to p transpose x, okay, you are solving for the coordinate of x. Okay, so this guy is just x, the coordinate of x with respect to this basis b, where b is equal to b1 and b2. Okay, so change of variable is the same as change of coordinate system. Hopefully you remember that when I take a vector, I want to find its coordinate with respect to b. I'm actually solving for this guy as a linear combination. Okay, you're trying to write this guy as a linear combination of these two guys. Okay, and what is that linear combination? So this is v1, v2, c1, c2. So, and this one is p. Okay, so your c1, c2 is going to be p inverse, but p inverse is p transpose. Okay, so p transpose x gives you those coefficients. So my y are just actually the coefficients in the change of coordinate system. So it's really this, okay? But it's up to you whether you want to think about it this way. Change of variable, same as change of coordinate. So now what I have is the following. If that one is y, this guy over here is actually y transpose. This guy here is actually y transpose. Y, you transpose this, you swap this and transpose both of it, it becomes this. So now my original thing, okay, my original quadratic form is now written, can be now written as this, which is y1, y2, d 3, 0, 0 minus 7, y1, y2, which become 3y1 squared minus 7y2 squared. Okay. So what is the significance of this thing? So let's talk about this more. Okay. Okay. So I also have some picture that I can show you later. 4, 6. Okay. I'm going to do part B. Okay. Okay. I'm going to work on B now. B is really just demonstrate to you why we do these things, why we do this substitution. Are you okay? I'm going to move on. Now this equation here now is essentially this guy set it equal to 16. Okay. But in part A, I did a bunch of stuff. And end up with 3y1 square minus 7y2 square equal to 6. Then it will be, this guy is equal to this, right? Now this is, of course, this is under some transformation. The transformation is y equal to p dx. Okay. Now I end up with this. This is a standard hyperbola. So you remember I talked about that earlier. Hyperbola is square minus a square y square minus b square equal to 1, right? So I just divide by 16 on both sides. Then I end up with this. So this is a hyperbola. So how is it related to the original one? Now after I do this, this looks exactly like this. Now it looks exactly like this. Okay? But the original one, the relationship between this one and the original one is through this transformation. Okay? This transformation, this P matrix, is the columns of the eigenvectors. So I'm going to show the picture from the book. Okay? I'm going to show you the picture from the book, and it will demonstrate to you what is going on. Yes, I need to show the picture from the book. I am going to share the screen and pull up the picture from the book. Okay. This is a picture I want to look at. Can you guys see my desktop? Are you guys able to see my desktop?
Yes.
So this is what happened. Okay. So the hyperbola look like this, but it's rotated from the original one. We redefine the axis, which is a change of coordinate. So this y1 and y2 are our eigenvectors. the direction of y1, y2 are our eigenvectors. Yes. So if you tilt your head so that now with the y1 and y2 axis, then this looks like the standard parabola. And everything is preserved, the shape and everything is preserved because it's an isometry, it's a rotation in this case. Because the matrix P is an orthogonal matrix. Okay, so when you mark around with this change of coordinate, we are not changing the length and the angles. Is it okay? Any question about this?
That's pretty cool.
I hope to a certain extent answer your question, Eva. Yeah, it's good stuff. It's pretty good stuff. Okay, so any question? We can do one more example if you guys like. Okay, because we have 20 minutes. Okay. We will do one more example. Hey, do you guys know how this guy look like? Y equal to 1 over x? Okay, very good. Right? Okay. We actually, some of you may be aware that this is a hyperbola. But this is not the standard position, it's rotated. We're going to just figure out what happened. What is the rotation and so on. We go through the process of what we just learned. Now instead y equal to 1 over x will be x2 equal to 1 over x1. Because of our rotation. Okay. So this one is x1 times x2 equal to 1. This one is actually a quadratic form. So what would be the matrix A? So we're going to say x transpose AX is equal to 1. But what is A? Are there x1 square term? Are there x1 square term? No. So it's 0. Are there x2 square term? No. So it's 0. This cross term is 1. The coefficient is 1. The cross term coefficient is 1. So what should I put in here?
1/2.
1/2. Now we're going to do the whole thing this time, okay? We're going to get the matrix P and the eigenvalues and eigenvectors and everything. Determinant A minus lambda I equal to 0. Minus lambda 1/2 minus lambda. Determinant equal to 0. Lambda square minus 1/4. Is that correct? I think that's correct. Lambda is equal to plus or minus 1/2. Then I try to get the eigenvectors. Lambda equal to 1/2. Lambda equal to 1/2. I will end up with negative 1/2, 1/2, 1/2, negative 1/2, 0, 0. RREF. You guys know what I did? I subtract 1/2 from this guy, from the diagonal entries, and then I solve this system to get the eigenvectors. So what do I get? I get basically 1, negative 1, 0, 0, 0, 0. So x2 equal to x2, x1 equal to x2. So V1 will be, is that right? Can you guys see that? I've skipped probably 5 steps there. But you guys are very good at this by now. Can you guys see this? 3 variable x2 equal to x2, x1 equal to x2, so it's 1 and 1. But I don't like it because it's not unit vector. It's not a unit vector. So do this. Is it okay? Lambda equal to -1/2. -1/2. Subtract by -1/2. 1/2, 1/2, 0. 1/2, 1/2, 0. We have 1, 1, 0, 1, 1, 0. V2. V2 will be x2 equal to x2. Oh, sorry, this is 0. x2 equal to x2, x1 equal to -x2, will be -1, 1. But this is too long, so we do this. So my P is going to be, my P is just this 2. What would be my D? My D is 1/2 and -1, sorry. Okay. So this guy, x1, x2 equal to 1. Okay. Now I'm going to do the, I'm going to do this y equal to p transpose x. Okay. Once if I do y equal to p transpose x, okay, because of this, x transpose ax is equal to 1. But A is P dP transpose. Okay. So this one is Y. This one is Y transpose. Okay. So I end up with Y1, Y2 here. D is this guy. Y transpose equal to 1. Okay. So I end up with f y1 squared minus f y2 squared equal to 1. And of course, now with this new coordinate system, this is a parabola, not parabola, hyperbola in standard position. So this guy is my y1, which is the direction of this guy. Okay, this is direction of v1. And this one is y2, the direction v2. Okay. Is it okay?
I have a question.
Yes.
Are quadratic forms when you make the matrix A, is it always symmetric?
Yeah. Yes, because you divide that cross term coefficient by 2. Yeah. You can probably recognize this is the thing for rotation 45 degrees. You guys remember cosine theta, sine theta, negative sine theta, cosine theta is a rotation. So this is a matrix for rotating 45 degree. Rotating 45 degree, and then you get the new axis. Yes, the quadratic form, that matrix is a symmetric matrix. I think you can, if you don't split it evenly, then it's not symmetric, but then it just hurt you, it doesn't help you. The symmetric matrix has a very good, properties. It used a lot in different things. Quantitative finance. We talking about the correlation between different assets in an asset class. Those are symmetric matrices. Data compression, symmetric matrices. We even talk about, on Monday, we talk about those linear regression stuff. The normal equation, that matrix is symmetric because we multiply by A transpose on both sides. So you end up with A transpose. ATA equal to ATB, right? Then this guy is symmetric. So symmetric matrix is very good, very important. So I'm actually done, unless you have questions. We're done with everything, basically. I am surprised we finished this actually on time. With next week's 2 days left to do whatever we want. What do you guys want to do next week?
Party.
Pardon me? What did you say? Review, okay. You guys want to do review? We can do review. And then you guys can come up with questions ready to ask. Okay. So we can do review next time. So it's good that on the week 17 we actually are done. Okay.
You transitioned very well, Professor. Good job.
Oh, you mean to the online? Thank you.
Yeah, that is true. Some of my other professors were struggling. You did a really good job.
Thank you. I am happy to hear that. I want to let you know that the school refused to reimburse me for the whiteboard.
That's so wrong.
That's so wrong. I mean, it's not a lot of money, but I mean, I just feel that in principle I should ask. And they say that it's not pre-approved. But what can I do? I mean, on Wednesday, I learned that we are going to shut down. And I was panicking to figure out what to do. On Thursday, or maybe on Friday, either Thursday or Friday, I went to buy the board. Okay, I don't have time to get it pre-approved. I'm just trying to let you know the school is not reasonable.
Oh yeah, we could Venmo you.
It's okay. It's not a lot of money, but it's just in principle. I think that they should reimburse me. Yeah, yeah. But they do compensate the faculties though. They compensate the faculty for some extra time. So they do pay us some money for the extra time to transition. Yeah, I just try to, when I transition, I try to make it as similar to what we have been doing as possible in terms of the same style. Because it's kind of hard to change the style completely. Okay, so we can even end a little bit early today, and then in next week, you guys think about what you want to do. Okay, so I can do some review. I can just keep talking, or you guys can ask questions. Which one do you like? You guys ask questions, I keep talking.
You can keep talking.
I can what?
You can talk, and then if people have questions, they can stop you, I guess.
Okay, okay, all right. Okay, since we have a little bit of time, maybe you guys give me feedback on the entire semester. In terms of the material, is it really hard? I mean, is it you guys don't complain too much. So is the material too abstract? I mean, do I do enough proofs, not enough proofs? Whatever you want to say.
I think I like the proofs because I don't know about a lot of the people taking this class, but I'm eventually going to have to do this again, but in a proofs-based class, right? So
Okay.
this was helpful. I got a little insight into what upper division linear algebra was like. So that, yeah, that was good.
Are you a math major?
Yeah. I'm gonna be taking linear algebra and real analysis.
Oh wow. Okay, so you are going to redo. You're going to redo. There's a proof-based linear algebra.
Yeah.
Are you transferring next semester?
Yeah. Transferring.
Do you know? You know where already, right?
No, I'm still deciding right now. Yeah.
Okay. Okay. Yeah, math major is good. I'm math major. So yeah, you have to redo this. So some proof those proofs will be helpful to you.
Yeah,
but
I'm saying because that's pretty specific to me, but I know there's a lot of engineers and taking these classes who don't necessarily need those proof-based type of stuff. So I think what you have now is a good balance. The majority should be the calculation-based stuff. I think.
Okay.
I think. Yeah.
Yeah, I thought it was a good mix as well.
Yeah, I have tried to do more proofs before, but students just stop paying attention whenever I put down the word proof there on the board. So sometimes I actually prove it without saying that it's a proof. But I do understand a lot of students want to get the mechanics right. Just to have the mechanics know what to do and what is important, what has significance and so on. Yeah. Okay. So if nothing else, we're going to just end 5 minutes early. So I'll see you guys next week on Monday then.
I have a suggestion too, but it's more like if there's time, like something that would be great because the course is already great is like more applications, or that's just like I like applications. I don't know about other people, but
Okay, so your suggestion is more applications.
yeah.
Yeah, the dilemma I run into is that I can't really finish the material. I already skipped a lot of stuff. So that I can talk about some of this stuff, which is a little bit closer to application. But then of course I run out of time. So
Yeah, that makes sense.
Yeah. So that's the thing that I'm struggling with mainly. Yeah. But I do agree that some of the applications are really cool. Okay, they are really cool. So they're used all over the place. How many of you are into machine learning? Computer science people? Yeah. Okay. Christopher say it's machine learning, right? So they use a lot of linear algebra. Okay, it's all linear algebra. I download an article, some kind of document from a UC on their machine learning class. That document saying that these are the math you need to know before you take this class, and it's 40 pages of linear algebra. So that's all linear algebra. Yeah. So it's used all over the place. Yeah. So those modeling we talk about, those least square modeling, a lot of times they just fit different variables to it and then see how well it fit. If it fit well, then they will use it. And of course, the machine learning, they can actually keep playing with the model to learn. Yeah. Okay. So any other things? Okay, so I will see you on Monday. Okay? Bye.
Bye.
Thank you.
Bye.
Bye.
Bye.